Alright, g'day everyone, how are we going? I thought I'd do this video for you to just more to clarify what's going to be happening throughout this simulation that we're going to be doing when I'm away. This is on Friday now. So this is our last mandatory practical. It's going to be investigating the photoelectric effect. I hope it's okay that you can't see me. I'll kind of just clarify what we're doing in the simulation and hopefully it'll all make sense. Now, number one, you're going to download this Excel document is kind of going to step you through it. So we've got an experiment page, but then also the analysis page. I'm going to be clearing out some of these numbers for you guys to do your own, but of course, if you're having trouble, you can copy my numbers to give you a hand. Number one, you're going to open up this link. That's going to bring you to the University, I believe, of Colorado or something like that. PhET, yeah, Colorado Education. And they've got this cool little simulation. You're going to crack it up and running. Step number two, you're going to set some kind of intensity. So you can see here we've got a couple of different dials. There's a battery that you can play with. There's a current, an amp reading. We've got some kind of wavelength that we can change. And then we've got the intensity. For this, I've kind of noticed that anything above 40% works pretty consistently. I'm just going to keep it on 100 for myself. The last thing you can do is also just change all the different kinds of elements here. And if you're feeling up to it, you've got a bit of time, you can use this last one to see if you can predict what that last element would be. Year 12s, if you get time, I would absolutely recommend doing that as good practice. Okay, but what are we doing? Now, the photoelectric effect tells us that if light comes on some kind of metal, okay, and it's got a strong enough intensity, that those particles, those photons, can hit those electrons and excite them, causing them to bounce off. Those valence electrons can generate a current. That's what we're hoping to see. Now, for the purposes of the experiment today, step number three, we need to make sure that this battery down here is set to 0 volts. So that means we aren't boosting the electrons. We aren't giving them any external power source. You can see if I increase it, they start to move a little bit faster. Their current increases. We don't want to do that. We just want the only energy that these electrons are getting is from the light source itself. So that's the only source of energy. Now our aim for today is kind of to generate some little graph like this. So you can see if I increase the wavelength, the amount of energy that those electrons are getting is getting larger and larger. We're going to try and imitate and create our own version of this so that we can calculate sodium's work function. That's what we're hoping to do. Now this is a really good practice that if we could calculate the work function and all of these different things, for today, we are going to do sodium, and we can find the error in our experimental analysis. But if you can figure out the work function for, say, an unknown metal, because it is a constant for each and every metal, well then, of course, you can figure out what that metal is. Okay, but we're trying to hopefully create some kind of graph like this. We're not going to need that one. Okay, so I've done step 3. I've made sure that my battery is at 0. That's sweet. I'm going to bring it down to this way. You can see the current is going lower, the less energy I give it because that wavelength is getting longer. So let's start there. Okay, we can see vary the wavelength until a current is generated. So until a current is generated. Alright, still 0, still 0. Oh, okay, we've got something. I'm going to go back down to the initial amount. So the smallest one, I can see 0.016. That's the smallest amount. Okay. Change the battery until the current turns back to 0. Okay, what I want to do is increase this slider now so that this current goes back to 0. The reason I want to do that is because right now those electrons have got enough energy that they can move across. I want to figure out how much energy exactly. So if I can do the negative, see how it's now gone to 0 there, alright, and the electrons, they don't fully go back to the anode, from the anode to the cathode, they stop and go back halfway. Okay, we want to figure out what is the minimum amount of energy required to activate them. In our case, it's the smallest possible amount, so negative 0.2. Okay, you can see in this example here, when it was whatever that wavelength was, we can't see it in the screenshot, a current of 0, there it is, was returned for negative 0.6 volts. Okay. So I kind of want you guys to have a bit of a play with the simulation first, but then afterwards I do want you to fill in this table. You don't have to use all of these points, but a minimum of 5 would be expected. So you can see I've already given you one for you. That this is all for sodium. You can choose a different element. For the purpose of the analysis today, I will just use sodium. And I've given you that first one for you, so 0.6 volts. was for a wavelength of 425. For this one, I've got 488. 488. And then the stopping voltage was 0.2. Okay, if I increase it now, let's go to there, 428. 428. And you can see I've already coded that to calculate the frequency for you. Just to remind you, the frequency, the speed of light is equal to lambda. I can't unfortunately do the nice math, but we know our lambda symbol, times by the frequency. So the frequency is just equal to the speed of light, that's c, divided by lambda. Lambda is our wavelength. So you just divide the two numbers. That's how we get frequency. Okay, so for 428, there's our wavelength there. I'm going to increase the slide. Oh, there we go. So something, still 0. Does take a little bit of trial and error. It was about, I think, 0.6 to stop that there. And that makes sense because this one is really close to this one here. So I may have had an error in this one. Not too sure. Oh no, that makes sense. That's okay. So go ahead, guys. Pause the video. Zoom ahead so that we can, once you've filled up this table, and then we'll jump back into it. Okay, hopefully you pause the video and you've filled in your table. I've gone into the analysis section, and yours probably looks a little bit different. You probably don't have a graph yet. I would have deleted that. Okay, but you've can now copy in all of your wavelengths. I'll keep the coding for the frequency. Now, this is not currently accurate. I need to turn to 15. Okay. A lot of all your frequencies initially will be really big. See how this is 7e to the power, times by 10 to the power of 14. So it's a really big number. And this one's not so big. It's just because I've divided by 10 to the power of 15. I don't really like working with those large numbers, so I just divided it out. But that's why I've included it there at the top now. So that should be on yours. Now the stopping voltage recorded as a positive. Those are those numbers there. And the way what we consider is that stopping voltage, that is the minimum amount of energy required in your electron volts, okay, for those electrons to have enough energy to start moving. Okay, so that's our stopping voltage. To convert that into joules, I'm just going to be timesing by the charge of an electron. Okay, so here we have those electron volts. That's what we recorded in our table. To convert to joules, you just got to get rid of that electron part. So you times by the charge of an electron. 1.6 times 10 to the negative 19. Okay, and you're going to get a little table like this. I want you guys to then plot your frequencies, keeping in mind that we have taken out 10 to the power of 15, just so that it looks a bit easier to read. And then our energy on the right axis, also on the vertical axis. Okay. Now what we want to do is we want to figure out the threshold frequency first. So let me step that out. I'll put it in here to find the work function. So that's what we're trying to do. We first need the threshold frequency. Okay, and the threshold frequency is the minimum energy required to eject electrons. So all of these different frequencies, these all ejected an electron. The ones before that, they didn't do anything. There wasn't enough energy there. To find the threshold frequency, we have to find the frequency when the energy is 0. That is the minimum amount. So following along, what is the minimum amount? Well, for those of you that are more mathematically minded, that is the x-intercept. Where is it? Where the energy is 0. So when it's just going to come off of it. Now we could use some more scientific knowledge just by estimating, I suppose, that would be about 0.6, but that's not very accurate. The way that we could do that is by adding a trend line, just like I've done here. Now, let's see if I can draw in some math to try and fill in the gaps a little bit for us. Our equation is y is equal to mx plus c. Yours might be a little bit different depending on the numbers that you collected. That's okay. So for me, I've got y is equal to 7e to the negative 19. It should be about the same just because we're all using sodium, I imagine. Oops, not a positive, it's a negative. I'll rub that out. Minus 4e to the negative 19. That e, just in case anyone's unsure, that just means times by 10. So it actually says 4 times by 10 to the power of negative 19. That's what that says. It's just a different notation. Okay, if we want to get the x-intercept, well, that's when y is equal to 0. So I'm going to substitute that in. Y is equal to 0, 7e, 19x minus 4e, negative 19. Okay, I'm going to bring this to the other side. I'm going to get my numbers on one side letters on the other. X is what I'm trying to find. So I will do 4, I'll just put it in a more normal way of writing it now. The negative 19 equals 7 times by 10 to the negative 19 times by x. Okay, so divide by 7 times by 10 to the negative 19 on both sides. Negative 19. That's all going to cancel out. Cancel, 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 cancels. Alright, those are even going to cancel too. So x is equal to, our x-intercept is 4 over 7. I will just quickly pull up the calculator. What is that? 4 divided by 7, 0.57. So can I rub this all out? No, Excel's not that nice. Let's just do it this way. That works. Cool. So in my case, the x-intercept was x equals 0.57. Now that's our frequency, so we should be using our units, but be careful because remember I wanted to make mine nice and pretty, so I got rid of that 10 to the 15. I'm going to put that back in, times by 10 to the power of 15. That's hertz. Okay. Now I've already got the math ready to go for the work function. Okay, but I'll just type it down here. So the work function, hopefully you remember from yesterday's lesson on Thursday, you've got h, that's Planck's constant, times by the threshold frequency. Now we've just found the threshold frequency. That was the x-intercept. So we could actually change that to be f0, f0. It's 0.57 in our case times by 10 to the power of 15. This is when I just quickly chucked it in. I just said it was 6, but now we've got a more accurate number. Let's calculate it. H is equal to 6.626 times by 10 to the power of negative 34. Okay. Be careful if you're doing it in Excel. If it doesn't like your negatives, got to put them in brackets. Look at it times by the fundamental the threshold frequency, 0.57 times by 10 to the power of 15. Okay, and that should be good to go. Yep, perfect. Now for sodium, the work function, the accepted work function for sodium is 2.3 electron volts. Now this is currently not in electron volts, this is in joules. Okay, so let's convert that. The way that we convert that is just by dividing by the charge of an electron. So divide by, in brackets, because Excel's not too smart, 1.6 times by 10 to the power of negative 19 is the charge of an electron. If you forget that, it's in your formula sheet. And there we go. We divide those two numbers. I'll keep that one there. But 2.36 compared to the accepted work value of 2.3. Awesome. And I've just asked you to finish off our analysis for today to calculate that relative error. So the measured, take accepted, divided by the accepted. So I'll give you a second to pause the video and do that. Okay. The measured is I'll just click it so it's accurate. That's our measured value. Our accepted is 2.3 divided by the accepted of 2.3 times by 100. We've got an error of 2.6%, which is really, really awesome. Okay, so hopefully you guys were able to experiment with the simulation today. Just got to play around, get a deeper understanding of what the actual photoelectric effect is. Okay, and maybe now you would like to do a couple of different elements, calculating their work functions. Maybe even doing this one here. You'll be able to generate the graph for yourself again just by sliding this. Even just by doing this, you probably can see that the threshold frequency is going to be, I don't know, maybe 0.8-ish. Okay, calculate the work function from that, and then you can look up a table of work functions. Let's just try that. Find our images, and then maybe you could compare it to some constant value. So finding that metals work function. All right, thanks very much, guys. I hope that was easy enough to follow. I'll quickly summarize if you've made it this far and just watch without knowing what you're doing. You're going to chuck under the simulation, chuck on the intensity, set the slider to 0. Vary that wavelength until you see a current down here. Okay, and now we do the battery, make it a negative until that current again turns back to 0, and that value is your stopping voltage. So all you need is that wavelength and the corresponding stopping voltage. Copy them into this table here and here. This will do the math for you in Excel. Plot those two columns. Find the x-intercept. Okay, because that's the threshold frequency, the frequency required to start ejecting electrons. Okay, and then the work function for the metal is by timesing Planck's constant with the fundamental frequency that you just found. Alright, hope that was easy enough to follow. Have a good one, everyone.